Okay, just a reminder that homework one is due tonight. I will hopefully homework two posted tonight. Due in 1 week. Oops, no. What? All right, cool. So last time where we had gotten to was the definition of the structure sheaf on spec R. So now I want to take spec R. This is for R, any commutative ring. And I want to think about this not just as a topological space, but as a ring space, a topological space with a sheaf of commutative rings on it. And so that requires defining the structure sheaf. And the sort of definition of the structure sheaf is on a distinguished open set. So remember, this is the set of primes such that F is not in that prime. So it's the set of primes where F doesn't vanish. I'm essentially taking F, I'm thinking of as a function, and I'm removing its zero set. Well, what does that do? That means on this open set, I can think of a function, an element of R as a function, but I can also think of the inverse of F as a function. So that means I take the localization of this algebra inverting F. So I get things of the form R divided by a power. Right, with the usual equivalence relation on these guys, which basically says multiplying fractions works like you think it does. All right. I mean, so I at some point was talking to a student about this and didn't find a truly definitive answer. But yes, I mean the term local ring comes from thinking about this kind of geometry. It seems to have come up a little earlier than things like the definition of schemes, but it was from that kind of world of thinking about algebraic geometry and thinking about what's happening close to a point. So now there are some things we need to check to make sure that this is sort of a well-defined thing. What do I mean when I write this? Right? I want a sheaf. So technically, when I write this, I mean that I mean if U can be written as the union of some dFIs, then O of X of U is equal to, maybe there's a better way to say this, right? I get elements of O of X of U by taking compatible elements of R of Fi for all I. Sections. part of Fi for all. And we should think for a moment about what compatibility means. So if I take d of Fi and I intersect that with d of Fj, so what does that mean? That means I have prime ideals that both don't contain Fi and don't contain Fj. Well, since it's a prime ideal, that means it doesn't contain Fi times Fj either. Right, so maybe a kind of nicer way to think about this is here I'm removing the zero set of Fi, here I'm removing the zero set of Fj. So if I take the intersection, that's removing the zero set of both functions, which is the same as the zero set of the product. Right, so the kind of thing you should think about, if I look at C of xy, let me not worry about other prime ideals. The maximal ideals in here give me a copy of C2, and d of x, that's the stuff where the x value isn't zero. That's kind of everything except this region around the x, the points on the x-axis. D of y is everything except the points on the y-axis. And so if I look at their intersection, that's equal to d of xy, the points where x times y are non-zero. Okay, so this consistency condition just means that if I take my element Ri in of I, and I have Rj and invert J, then when I map both of these to R invert Fi times Fj, they have to have the same image. So this is a little bit weird. There's sort of a consistency I need to check to make sure. So, right, I'm being a little vague here. I say I get elements of O of xu from this. Here I'm sort of applying the idea that I need to get a sheaf, right? If I have a sheaf and I have that on this open set, elements of R of F give me sections, then whenever I have compatible sections, they have to glue together to give me an element of the whole ring. So this is a form of sheafification. But I want to check something important, which is that I don't, on the whole space, get any new sections by doing this. So can I get sections of O of x of x itself by some sort of weird unexpected gluing that don't come from R itself? So what I'm really saying here is I haven't actually proven for you that a sheaf with this property exists, right? This is what I would like to happen. And there's sort of, since I'm only talking about a basis of the topology, I don't get to say yet, this gives me a pre-sheaf. But if you wanted to, you could figure out what it meant to give you a pre-sheaf on a basis of the topology. There is sort of a natural way to assign to a basis of my topology sets, or in this case, rings. I, of course, have a restriction map, which is, give myself space. So what I'm saying here is I want a sieve such that if I take O of X, E of F, yeah, R of F, and such that, so what happens if I have that D of G is contained in D of F? Right, so in this case, G is 0 everywhere that F is 0, but maybe it's 0 at more places. Yes. Okay, so what am I trying to, I'm sort of backed myself into a corner here because I didn't go through all these details in Vakiel about how to construct a sheaf from a sheaf on the base, on a base of the topology. So I fear now that I'm making this more confusing than it needs to be. But there are two ways to think about this. Okay, one way to think about this is I declare this is what I want to happen. And I say, okay, well, these sections exist. And I'm going to make a sheaf where I just say these sections exist and whatever else follows from the sheaf axioms holds. Right, so you could imagine using like problem 1 on the homework to construct the espace-totale and saying, well, the sections are continuous sections of this topological space, whatever they turn out to be. Okay, another way to do this, which is sort of what Vakiel does, is instead he says, okay, I want to define a sheaf, but I only want to tell you its sections on a basis of the topology. Now there's some consistency I need to check if I'm going to have such a sheaf exist. And what is that consistency? I need to tell you when there's an inclusion of two bases of the two open sets in the basis, what's the restriction? So that's what I was getting to here. This means that G vanishes anywhere that F vanishes, and it might vanish at more places. So what this means, so this is an exercise in Vakiel. I will leave it to you as an exercise in ring theory. So I would hope that this means that G is divisible by F. That's not quite right. It's actually that G to the N is divisible by F. All right. But this means that if I have some fraction A over a power of F, right, then I can use this equation to write it as A R to the M divided by G. So this is my restriction map. It's just the obvious map between localizations, where I use that I can write F is equal to C to the N over R. Or better yet, 1 over F is equal to R divided by G to the N. So it's just whenever I have one of these open sets, have a restriction map on the sections. And then what do I need to check the identity and gluing axioms? Well, the identity axiom is pretty easy. So identity on a base. So I'm going to write everything in terms of DFs and DGs, but this is all just general stuff about if you have a base of the topology, which is if I have a set in my base and I write it as a union of other sets in my base, which certainly I can do sometimes, then if I have F in what I want to assign this F or this S. So this is in or invert F. And S restricted to all these open sets is 0, then S is equal to 0. All right, so how do I prove something like this, right? This is something I genuinely need to worry about because I can do things here, like take my X to be spec of C of XY mod X times Y. Right? And I can look at D of X plus Y. Where's that 0 on here? So now I'm just taking these coordinate axes. So if I remove where X plus Y is 0, I remove the origin. But I can also write that as D of X union D of Y, right? Which are, this is D of Y, the points on the X axis. Sorry, not this. Yes, D of Y. Right. No, sorry, this is D of X. D of X is the points where Y is equal to 0, but X is not 0. And D of Y is the Y-axis, the non-zero points on the Y-axis. So you can have interesting unions like this. And the map from this guy minus the origin going to D of X, that's not going to be an injective map, right? So the function Y gives me a non-zero function on the union of these two guys. But it becomes 0 if I restrict to D of X. It's just not 0 if I restrict to D of Y. So I really can have things that are killed by one of these maps, and I want to prove that I can't be killed by all of them. All right, well, I have to use this property. Why is this true? Well, if X times Y is 0, then 1 of X or Y is 0, right? I mean, like, look at the picture. This is D of X plus Y, right? If X times Y, if 1 of X and Y is 0, and X plus Y is 0, that means X and Y are both 0, right? And D of X is this stuff, D of Y is this stuff. Okay, so this is just kind of the first example you should worry about of this kind of thing can happen. And there's something non-trivial to check, that I can't be zero on both of these open sets. I can be zero on one of them, that's fine, but I can't be zero on both of them. All right. So imagine this does happen. So I have some S. So this is going to be in RF. And if I think of S in RFI, then I get zero. So what this is saying is that this guy is equal to 0/1. And if I go through my equivalence relation for when elements of this localization are zero, this means that some power of Fi times S is zero. That's what it means to be zero in the localization. Right? So for example, here, how do I sort of see that the image of X and when I restrict it to dy is zero? Well, it's because X times Y is zero. So if I declare that Y is invertible, that can only hold if X is zero. This is sort of the thing that can go wrong in these localizations is when you declare one thing to be invertible, that can force something else to be zero. Okay. Now I have to use this property. What does this property mean? It means D of F is equal to the union of these guys. So as we talked about, that means that in this localization, I can take one and write it as the union of some bi times fi. Let me call this the n. I have to raise things to ni. Okay. And here, the bi's are in R. Okay. So now what happens if I multiply this equation by s? This is sort of the trick you always want to use. You write one this way, and then I multiply by s. And I get that this product is equal to this product. Well, but the right-hand side is zero. It has f times these powers of fi in them. So my original s was zero as an element of Rf. So this is, again, this sort of partition of unity argument. Um, uh-huh. No, but this equation only involves finitely many of them. So, I mean, I could take any powers on the FIs I wanted, and I would still get this, right? Because what I'm using is there isn't any maximal ideal that contains all of the FIs. Well, if I take powers of the FIs, they still aren't going to be in that maximal ideal. All right, cool. So this shows this identity property that I can't have something on here that restricts to zero on each of these open sets. And that sort of that sounded like this totally trivial thing when we defined sheaves, but we sort of see here, oh, this isn't as trivial as it looked at first. All right. Yeah, exactly. I was using this property. So as we discussed last time, what does this mean? This exactly means that for any maximal ideal of Rf, it does not contain one of these Fi's. And so the ideal generated by the Fi's or any powers of the Fi's isn't contained in any maximal ideal. So the only possibility is it's the whole ring.
Last time we used that there for union reduction.
Yeah. Well, I mean, remember, this is homeomorphic to spec of Rf. That's what I'm using. As usual in Vakil, he sort of goes through the argument for all of X and then says, okay, exercise, do this for a distinguished open set. But it's really the same argument, but you're doing it in the localization. All right. So now the other important part of this was identity on the base, gluability. I mean, probably wasn't the word that Vakil used, but you know what I mean, glue. So what does this say? This says, again, if I have this property, that D of F is a union of guys in the base, then if there exists SI in D of Fi, sorry, in say R of Fi, such that, so, right, the property I want is that if I take SI and I restrict it to D of Fi intersect D of Fj, then that's the same as Sj restricted to the same guy. But let me just remind you, right, this means that if I take SI over 1, that should be equal to SI over 1. And this is in R invert Fi times Fj. So for example, in this example, what happens if I look at the overlap between dx and dy? There is none, right? If I call this R, if I invert x times y, I've killed the entire ring. I mean, usually we say that you shouldn't try to invert a zero divisor, and this is exactly why you get into trouble here. So if this is sort of by the usual definition, not even a ring, because it doesn't have an identity. I've set 1 equal to 0. I'm kind of not really supposed to be able to do that in a unital ring. Well, in the abelian group 0, I mean, if you want to get very fancy about it, does have a unital ring structure where 0 is also the unit. Yeah. Yes. Yes. I mean, somehow you don't have something you can assign to the empty set if you don't let yourself think of 0 as a unital ring. So you kind of need it. All right. I didn't finish my sentence here, such that then there exists S in R of F, such that my SIs is restricted to D of Fi. Okay. So we didn't really need to use this here, but there's sort of a little bit of annoyingness about the fact that this cover could be infinite. That's a possibility you should have in mind, that there might be infinitely many efforts. But of course, we learned last time, and we see the proof right here in this formula, that spec of a commutative ring is always quasi-compact. So even if I have an infinite number of FIs, actually, there's going to be a finite subset of them that form a cover. All right. So let I sub 0 in I be finite, such that d of f is equal to the union just over this I0 of d of f. And such a thing always exists. All right. So I end up with this kind of complicated thing where I say, okay, I let my SI be AI divided by FI. Now, in general, I should be putting a to the MI here. But what I'm going to say, just to kind of keep my notation simple, is, well, I can always replace FI with a power of FI without changing anything, right? I won't change this property. I won't change that this guy lies in the localization. So replacing FI with a power doesn't change anything. So I can keep my notation simple and assume that SI is just alpha I over FI. All right. So then this equality becomes that if I take AIFJ minus AJFI, then some power of Fi times Fj to the M times this guy is equal to 0. So again, this is a little bit annoying to have this power here. So I can use my freedom again. I can always write AI over Fi is equal to AI times Fi to the M divided by Fi to the M plus 1. And there's nothing special about when I replace Fi with a power, and there's nothing special about A. So I can just make this my new AI, and I can make this my new. And by doing that replacement, I can assume that I don't have to put this power here. I can assume that I just have AI J is equal to AJ. Oop. Okay. And now I play the argument I had before. Right? I say, well, I chose this finite set so that it was a cover. And again, using my freedom to always replace Fi with a power. No, I don't even need that here. I can write 1 is equal to RIS. All right, so what I'm doing here, I want to use this equality in a slightly different way from before. So ultimately, what I'm trying to do is I'm trying to find some R over F that this guy is equal to for all I. How am I going to do that? Well, I want a sort of A over F here, right? And I can multiply it by this equation. I'm just sort of imagining that such an A over F exists. What would it look like? And then I would say, oh, right, my A over F, it's equal to this guy as an element of the localization at Fi. So this is actually equal to AI over Fi. Oh, great. So my Fi is going to cancel. All right, it's just sort of something made me slightly unhappy about. Well, I mean, right, yeah, okay. Yeah. Sorry, the thing that threw me off here is the RIs, these are in R localized at F. So that's where the localization over F might come. Okay, good. I erased my stuff too soon. So the kind of thing to imagine here is I have an A over F here, or A over F to the M. And that's going to be equal to this Ri times. So I can replace this guy by AI over Fi, and there's an Fi here. So this guy should just be equal to Ri. And this is the sum over I and 0. Okay. So this doesn't make any sense because I didn't know what this thing on the other side was. But I can just forget about this guy. And I can just declare, okay, consider the element R, this is in R of F, of this form. Right? That's a perfectly consistent thing. Right? And then I can look at the equation that I just had and say, oh, that actually tells me that I can rewrite this guy. So if I think about R divided by 1, now I'm thinking about this in R invert Fi. I can think of this as Ri times AI. But then in this localization of Fi, I can use this equation. Let me, as I fixed I here, let me make my index A of RK. Okay. And I can use this equation, right? If I rewrite this equation, this tells me AK is equal to AI divided by Fi times Fk. And this is equal to the sum over these Ks of RK times Fk times AI over. Okay, great. And this sum is 1. So this is just AI. So this means that R is my desired element that glues all of these sections together. So I use the fact that I could get this equality for 1 to allow myself to sort of remove the denominators one by one. The fact that I have this Fi here lets me cancel the denominators out of these guys and get my guy to glue together. Now you'll note here, I only did this for this finite subset I0. So what about all the other elements of I? Well, I found the section that I want, and now I just have to check that it's not inconsistent with any of the other elements of I. And that follows immediately from this, from the identity. So since we have already used up a lot of the class, let me just say consistency with other i's follows from identity. Right? That identity axiom tells me that this R is actually unique. Couldn't find any other element that would be consistent with all of these guys, or that identity thing would fail. Yeah. Yes. Yes. Because DF as a topological space is quasi-compact. Right? It's exactly the same argument of if D of F is equal to this union, that exactly means that the Fi's in the localization R sub F generate the whole ring as an ideal. So, you know, yeah, I mean, it's right. The relevant kind of open cover is of that open set. So just thinking of that open set as a topological space. But that open set as a topological space is spec of R of F. Yeah. By this restriction map I wrote here. Yeah. Yeah. I mean, if you think about this, this is like I'm taking a function on the union of these two coordinate axes minus the origin, and I'm restricting to the two ones separately. So the two separate maps will have a kernel. And it's genuinely kind of not totally obvious that if I have a Laurent polynomial in X and I have a Laurent polynomial in Y, I have an element of this quotient that sort of glues them together. If you want to think about this carefully, I think I got this right, that if I have a Laurent polynomial in X and I have a Laurent polynomial in Y, then the way to glue these together is to write, so X divided by X plus Y is the function that's all one on the x-axis and 0 on the y-axis. And y divided by x plus y is the function that's 1 on the y-axis and 0 on the x-axis. So this goes to f of x times x, g of y times y, divided by x plus y. So if you think about what happens when you restrict this to the x-axis or restrict it to the y-axis, you get back these two functions. Right? And so if you went through this proof, in this case, this is what it would tell you to do. All right. So now that sort of establishes for us, so this tells us, theorem, there does exist a sheet on spec of R equals X, such that when I take O of X on a distinguished open set, I get exactly this localization. Okay. Now, what about other open sets? There are open sets that aren't distinguished. So what happens on those? Let me just do a couple of examples since I have a little bit of time left in class. So for example, the kind of canonical example of an open set which isn't gotten by inverting one function is if I take spec of C of xy, right, and I remove the origin, which I think of as the maximal ideal generated by X and Y. So this spec is often called A2C. But remember here, I'm also including the points for non-maximal ideals. But I'm removing exactly this point corresponding to this one maximal ideal. So you should think about this as C2 minus the origin. And then I also have all the other prime ideals, but let's not worry about those guys. You'll note that those closed subsets, you don't get rid of any of them by removing the origin, right? Any closed subset that isn't one point will still survive when I remove the origin. So I don't need to get rid of those other primes. So yeah, let me call this U. What happens if I take O of X and I look at it on U? Well, what should I do? I should take U and I should write it as the union of two distinguished open sets. And I can do that. This is going to look a lot like that example with the coordinate cross. It's dx union dy. But now because I have the whole plane, I'm not getting something I can write by inverting one function. There's no polynomial function that only vanishes at the origin. In complex analysis, that's called Hartog's theorem. Right? You can, in a higher dimensional complex space, you can never have an isolated zero of a polynomial, or more generally, a holomorphic function. Okay, so I should look here. This is choosing a section on d of x and a section in d of y, such that when I restrict these to the intersection, to d of xy, these guys are equal. Okay, well, unlike that situation with the coordinate cross, this is a domain. So I'm never going to set something to zero by localizing stuff, right? A domain injects into any of its localizations. So all these kind of concerns we've had about localization setting stuff to zero, that was only really relevant in rings that aren't domains. But we want to have rings that aren't domains, so they're still important to worry. So here I have my ring R. I'm looking at its map into R of X plus Ry. Well, that's already injective. And I'm looking for things which are consistent when I go to R of xy, but all of these maps are injective. So if two things in here agree when I go to R of xy, that just means they're equal as elements of the fraction field, right? Sort of all of this sits inside the fraction field of R. So this is just equal to, as subrings of the fraction field, Rx intersect Ry. Well, that's just R. Right? If I take a rational function and I write it in least terms, well, if its denominator has to be divisible by x and, it can only be a power of x and can only be a power of y, the only thing it could possibly be is 1. So this is actually equal to, if I take the functions on the whole space. So there's sort of no new functions I get by throwing this origin out. And this is sort of a general principle. You have to be more careful about this when you're thinking about singular things and such, but removing stuff that's smaller than a distinguished open set, or sorry, the complement of a distinguished open set, but sort of smaller than the zeros of a function, shouldn't give you any new sections. You have to be careful about this for singular guys. For smooth guys, that's actually a good principle. Oh, shoot. I'm basically out of time. Let me mention one more example, which I'd gotten to at the end of class last time. So another sort of thing I can think about is what happens if I glue two copies of this together. So if I look at R equals C of XY ZW, and I put in the equations XZ, XW, YZ, YW. So what this forces is either both X and Y are 0 or both Z and W are 0. So this is this guy I mentioned last time, spec R is equal to stuff where the first two coordinates are non-zero, but the second two are 0. And these guys. So there's a U here, which is spec of R minus, again, the origin. So this is basically taking this coordinate cross picture and kind of doubling everything up. Instead of just having one coordinate and one coordinate, I have two coordinates and two coordinates. But I get a similar kind of picture where when I remove the origin, then I have a disconnected set where either one of these guys is non-zero or one of these guys is non-zero, and they don't meet anywhere. So in this case, if I look at O of X on U, well, I can choose a section where these guys are not 0. I can choose a section where these guys are not 0. And there's no consistency required between them. So this just becomes two copies of my polynomials in X and Y plus polynomials in Z and W. And I don't have to make any kind of consistency between these. In particular, I can do things like take the constant function 1 here and the constant function 0 here. And that's a perfectly good element of the structure sheaf applied to this open set, which is a little bit strange. In particular, this guy is not a localization of this ring. Yeah. Yeah, this is right. This means the ideal X, Y, Z, W. And so for the same reasons that the origin can't be cut out by a single function here, there's no single function that picks out this guy as its 0 set. Right? If I take any polynomial in the X, Y, Z's, and W's, like on this set and on this set, I'll still get one-dimensional subvarieties, or the whole thing. And so I can't pick out this origin with a single function. And I can see that here by what I get when I do this, right? So an element of my ring, of course, gives me an element here. But the map just isn't surjective, and it can't be made surjective by doing some localization. There's no element of my ring that becomes invertible here. I just have more stuff. All right. I'm afraid that's all I have time for. So we'll talk more about schemes next time.